Midterm 1 is when? Which is a week from Tuesday, a week and a half. Okay, we're almost there. So, some of you, again, ad drop finished what, yesterday or something. Some of you have never met me before and are here for the first time. People keep moving in and out. That's just what happens every semester. Don't worry about it. But we got a midterm in a week and a half. All right. So, exams, it's funny. Math is about thinking. Exams are not about thinking. You should not have to think on an exam. On my exams, some exams, if it's a timed exam, like what we're learning took human beings thousands of years to figure out. And each of the little steps that we're taking every class is like 100 years. Okay. So I will not be asking, I don't think it's reasonable to say you got 80 minutes to figure out something that took people 100 years to figure out. That's not what an exam is. That is what math is. Math is learning and struggling and finding new ways, better mouse traps. This is except calculus mouse traps, whatever, trapping intervals or something, whatever. An exam is mastery of skill. There are skills we're going to go over. We haven't learned all the skills that we need for the midterm. The lecture in 1 week will be a review of all the skills I expect you to have solid by the midterm. See, every single person here can and should get an A. All you do is you get the skills, you solve every problem. That's it. I can't, I can't do anything but give everybody an A. That's it, right? You guys want a grade. I want you to learn information, skills, and not just skills, but enjoy the process of learning mathematics, figure out how it comes about. So exams measure skills. Can you compute a tangent line to this curve? Can you, do you know your sine functions inside and out? Do you know your exponentials? Do you know your logs? So that's what's going to be tested. That's the only thing I can test. I'm not testing how smart you are. I'm not testing how talented you are. I don't have the methods to do those things, and I don't care. I want to know skills. Can you do this or not? Yes or no? Here's the problem, solve it. Okay. So really, if you like 80–90% of you are doing all your homework, everything's coming in. If you're in that 10%, like, what can I do to help you? I'm here to help you develop those skills. Please come to me. A lot of you are coming. There's a lot of you that are coming to office hours. There are a lot of you that are just writing me emails and asking questions or scheduling another time to talk either in person, over Zoom. All of that is great. Let's do that. Let's do lots of that. What are things that, so I don't want 10% of you not to get the skills. I want 100% of you to get the skills. So if you're in that 10%, tell me what I can do to help you. What are people finding useful? Are the homeworks a good way to learn and like really drill and practice? And are you guys like, I don't know, do you just do the homework or do you do it together with other people? Like what works? Annabelle, can I pick on you? Yeah, I'm picking on you.
We do it on our own and we can figure out.
Okay, so okay, great. So you work on your own, but then you text and chat when you, do you guys have like a Discord server going or something? Do you have a Slack channel? Like what? I just say these words. I've never used Discord or Slack. It's just an iMessage. Great, but you have a community. You have someone that you can go to. That's so important. The way to learn math is to talk to other people. If you can teach someone a concept, you understand it, right? So please get into a group where you can text somebody and say, oh, I don't know, what's going on with this problem? Why isn't the computer taking my answer? What am I doing wrong? Right? That's what's going to help you get through the homeworks. Are people able to, so other than Annabelle, can I pick on somebody else or can someone volunteer? What's working for them? Tell me again. Naban.
I usually do the question and then do it.
Awesome. So you might do a few extra problems that aren't assigned. Awesome. So that's a great point. Even if you manage to solve the problem, like the first time you solve a problem, you're like, wow, that was hard. I wonder if I'll be able to do it again if that same kind of problem appeared on the midterm, right? So what should you do? The computer will spit out. How do you find new problems? The computer tells you? You just click a button. Okay, beautiful, beautiful. This is what you paid the $100 for, to have a button. Eventually, I mean, they're going to charge you, right? I don't know. Maybe you guys have better ways of getting these products than I do. But there's a button that you can press that will get you more questions of a similar nature. And it's really, I can't stress this enough. A skill like driving is a skill. The first time you sit there and someone shows you what to do, even if the driving instructor is in the passenger seat and you're the one doing it, they're still telling you what to do. Like, I want to get to your 100th drive. Then you I just tell you, go, drive around the parking lot and do a parallel over there. You're like, yeah, no problem. I've done this 100 times. Boom, boom, yeah, park. There's your license for it. That's exactly what a test should be, a stamp of the skills that you already have. Not new problems, not things that are confusing. You should just be like, yeah, I got this. Here's how to do it. Done. Give me my A. Right? That's what we're going for. If you're not there, that doesn't mean you're a bad person. It doesn't mean you're not smart. It doesn't mean you don't have the talent. It just means we need to figure out something else that's going to work for you. So come to me. Like, if you're scared of me, I'm a scary guy, right? Go to your friends. Go to the help center. Go to the learning center. Get the free tutoring that's provided. Like, all of those things are there. A week and 3 days from now, if I'm computing that right, Monday night before the Tuesday midterm is too late to start thinking, oh crap, I don't really know this stuff. You will not learn it in a night. It takes little drips of learning day after day after day to accumulate that skill. Okay, deal? Okay, I'm off my high horse. Let's get back to math. So, yeah, I've said enough. Okay, come to me if you have questions. Peter.
Yeah. Office hours.
I do not have so office hours are Tuesdays, but shoot me an email. Shoot me an email. We'll set up a time either in person or over Zoom.
I just have a few questions.
Sure. We can chat after class for a few minutes if you want. Yeah. Like, my job is to help you guys. Just 1 second, Janini, and tell me one more time. Align. The exam is in class. Yeah. Tuesday in class. Janani, right? Janani. I have to put the accent on the right syllable. Janani. Yeah, great question. Is the exam going to be more like the My Math Lab problems or more like the assignments? The assignments, it's going to be a mixture. The assignments are testing, do you understand what the fundamental materials are asking you? Can you write a sentence to explain what is a limit or what is a tangent line? And the homework questions are saying, can you compute this? So both of those are skills that I want you to have. Okay, probably it's going to be much more centered on, there's only so many free response questions I can ask in 80 minutes. But I think it's perfectly fair game to say, what is definition of, what does it mean for a function to be, we're going to talk about continuity today. So I can say, what does it mean for a function to be continuous? And you should be able to explain in words. That's not a computation. That's a, do you understand what the thing is? So there's going to be a mixture of, I want to know both of those things. So having the skill for writing an answer to a question like that is what you develop in workshop. Okay, there's both of those things are important. Knowing what's going on, having the skill to express yourself and explain what's going on, and computing. Zain. Yusuf. Where's Zain? Okay, I was close. You don't need a there's not going to be anything that you don't need a calculator for this. Just pen and paper. I'm not going to ask you to multiply big numbers. I'm not going to ask you to, yeah. You can compute. You can compute numbers. You don't need calculators. Compute numbers for you. You don't need that. Okay. I do want you to know what a sine wave looks like without needing to graph it. Ying, just a second. One more time. Nimmer.
Yeah. It's the first exam. I'm taking most of the people.
The exam is not going to cover the pre-calculus review, but it will involve the pre-calculus, what that means is on the exam, it's fair game to ask about the exponential function, about logarithms. I assume those things are already there. So it's not quizzing pre-calculus topics, but those pre-calculus topics will appear in the other kinds of questions. So it'll be crucial that those things are solid to do anything, but I'm not checking if you, there won't be questions specific to it, but everything will involve those concepts. Yeah. Ying?
Will you provide some scratch papers and some other mark?
There's going to be plenty of paper for you to write on. Yes. Yeah. One more time. Keel. In the midterm?
Yeah.
Somewhere between 2 and 100. What difference does it make? Right? There's questions. It's a time test. So in some sense, I am checking how quickly you can solve problems, only insofar as you got that driving test and you got to park, and I don't have all day for you to make these micro adjustments as you try to parallel the car back. Like, you should have the skill to pull it in. If it takes you 5 minutes, that's okay. It should really only take you 1 minute. I'm not testing the speed at which you do things, but having fluency means that you are able to solve problems within a certain amount of time. Okay, so it should not be overwhelming. I expect some people to finish early, but I'm not testing you on how fast you can write. I am testing you on whether you have these skills under your belt. Okay, on to math. Going once, going twice. Will? In my math level, you have a practice evaluation. You mean like a practice midterm? We're going to do a practice midterm. There's a whole document we have prepared for you guys, which is like, here's a whole bunch of problems that are reasonable problems to have on the midterm. And we're going to go over that document altogether. Yeah. My job is to prepare you guys for this thing and give you all the skills you need. Your job is to do whatever you have to do on your end to actually, again, I can't make your neurons beat at a certain, I can jump around and be a monkey up here and try to encourage you to do things, but at the end of the day, you have to get the skills. I can't give you skills. Let's go. Let's go. All right. Where were we? Limits. Oops. There we go. Okay, limits. Where do we leave off? Right. Okay. So an important concept. We started talking about limits last time. So recall that when I say what's the limit of something, a limit does not care at all. The limit does not care at all. A limit does not care at all. A limit does not care at all about the value of whatever it is, whatever function you're thinking of your function at the point. In other words, let's just do an example. Here's an example. Here's a function. So here's I don't know, 2 or something. Here's x equals 2. And I'm giving you the graph of a function y equals f of x. Okay, and we go like this. When we get to 2, we jump like this. I don't know why, but that's the function. Okay, that's the graph of some function. All right. So if this is our graph, so for this function, can we say what the limit is? What's the limit as x goes to 2 of f of x? Same, don't tell me. Yusuf?
Yeah.
Yes.
Doesn't exist, right?
It doesn't exist. It doesn't exist. There's a different limit from the left and from the right. Okay, there's a different limit from the left and the right. So How do we do, do you guys know about left limits and right limits? Have we talked about this yet? What's the limit of f of x as x goes to 2 from above? So that's from above. As you come down from above 2, that's what this plus sign says. Value is greater than 2, Shreya. It's 3, exactly. This limit does exist, it's equal to 3. The limit as x goes to 2 from below of the function is, as I go from below, it's 1. The value of the function, f of 2 itself, is 2. This says what is the value of the function? It's literally 2. And the limit as you approach 2 does not exist. Okay, so when I say a limit does exist, so if limit as x goes to c, some constant c, right? Like this doesn't have to be 2. This is like whatever constant you want of a function. I guess I should say for the limit to exist, for the limit to exist, you need a limit from below to exist, limit as x goes to c, well, let's say from above. So the plus is that you make c a little bit bigger. That's how you remember whether it's from above or below. Make c like values of c that are greater than, values of x that are just greater than c, coming down to c. You need this to exist, and the limit as x goes to c minus to exist, and they have to be equal, and they're equal, and they agree. Okay, so that's what we mean by a limit existing, is if you go from the left and you go from the right, they're both agreeing on the same thing. Okay, does a limit from a left always have to exist, or from the right? How could you have a function where it doesn't have a limit as you approach, some value? Same, Yusuf, tell me. Nimmer.
If the function is also not approaching.
If it, yeah, like how could I possibly draw something that's not approaching anything from the left to right? Anybody know of a natural function that does this, Ying? So it could be the denominator 0. That's true. That's absolutely true. Okay, so how could ways for the limit as x goes to some number from above not to exist? Well, okay, one thing that could happen is just there's no value above c which is in the domain of the function. So there are no values above c. One more time. Bible.
Can you make like a square root graph?
A square root graph. So a square root graph is a great example of this kind of thing. So that's this is Vaibhav's example. What is the limit as x goes to 0 from below of square root x? Well, what's the graph of the square root x function? So yeah, sideways parabola, but just the upper piece of the sideways parabola. So what happens? What happens to the values as we approach 0 from below? Bless you. What values are we seeing? We're not seeing any values. It's just completely outside the domain, right? So that's one way for a limit not to exist. Bless you. So this is one example. This does not exist because there are no values in the domain. What else could happen? Ying said it could go to infinity, right? Like if I take the limit as x goes to 0, let's say from above, of the function 1 over x, we're getting a little ahead of ourselves because we were going to talk about infinite limits later. But what is this Anybody know what y equals 1 over x looks like? Yeah, the hyperbola, exactly. One more time, your name? Julius. Julius is saying it looks like a hyperbola. That's exactly right. It looks like that. This is y equals 1 over x. So what happens as we approach 0 from above? As we approach 0 on the x-axis, the y-axis is just blowing up. It's not converging to a real number. Okay, so the limit does not exist. This limit we say is equal to infinity, but infinity is not a real number. It's just blowing up. So again, I'm getting a little ahead of myself about saying this, but I think you guys understand intuitively what this is supposed to mean, which does not exist. In other words, infinity is not a real limit. It's not a real number. What number is infinity? It's not a number. So when I say is equal to infinity, that doesn't mean that a limit exists. It means that the value just gets larger and larger and larger and goes up. Does that make sense? Okay. Is there another way for this limit not to exist without blowing up and without being undefined? Zane? Beautiful. It could be oscillating. It could be oscillating. I mean, there's all kinds of, these are just some of the ways, some ways for a limit not to exist, even a one-directional limit. It could be oscillating, oscillatory behavior, oscillatory behavior. For example, anybody know this is like a function that in math is very notorious? Julius. Beautiful. Oh, wow. You got it. I didn't know if you guys would know this function. Yeah. It seems like a very innocuous function. What could possibly go wrong? I'm taking 1 over x. Sine is a trig function with a polynomial, not quite a polynomial, a rational function, a ratio of 2 polynomials. Like this seems like a really reasonable function. But if you think about what's going on, you're plugging sine into values that are getting larger and larger, but sine is going up and down. So as you get larger and larger, you keep spinning more and more. So let's see this. Has anyone seen a graph of this function other than Julius? Have you seen a graph of this thing? Yeah, Julius has seen it. You guys want to see it in action? Let's see. Let's test my Desmos. Sine of 1 over x. Yes, exactly. That is exactly the right reaction. So the sine function, if I start trying to see what's going on here, you see the thing. It's just oscillating. So as I get closer and closer to 0, I'm just bouncing back and forth, and there's no way to make sense of a limit there. Okay, it's undefined at 0 because I can't take 1 over x. So it's not defined at 0, but near 0 is just all over the place. It has no limit. Okay. So let's record that. So undefined, undefined at x equals 0. That's just not in the domain of the function. I can't take 1 over 0. But near 0, it looks like, it's doing something, and then it's just, and then it keeps doing that on the other side. Okay. Question? Yes, Jenny. You need to. Yes. So let's write it explicitly. The limit as x goes to 0, either from above or from below. Let's say from below, of sine of 1 over x. This does not exist. I guess I wouldn't say it equals does not exist. It just does. This limit does not exist. Doesn't matter. You put the equals in. Okay, does that make sense? Here's a question. Is this function even or odd? This would be a great midterm question. Is the function sine of 1 over x even or odd? The only function that's both is the 0 function. So which is it? I've drawn it in a weird way. It's hard to, I just drew it by hand. What does it mean to be even or odd? So this is an aside. If I take sine of 1 over negative x, in other words, if I take this function, I replace x by negative x, do I get something related to the original function? Yes, exactly. This is an odd function of x. This is an odd function of x. The composition of two odd functions, the minus sign moves out of the first one, moves out of the second one, all the way out south, right? So you get minus sine of 1 over x, which means this function is, so sine of 1 over x is odd. Okay, just a little test of your, this is pre-midterm review. And if you look at it here, okay, this will give it away. You see how it goes up there, but down here. So it's got that rotational symmetry, not the mirror symmetry across the y-axis. Okay, good. Yeah, any questions? Good, okay. What else? Okay, so that's a little bit about limits. We're gonna do much more on limits. Today is a more serious exposition of limits. Good. So most nice functions, I mean, even this function, which is not nice at 0, out away from 0, the function is continuous. So even this bad function, even this, sine of 1 over x, away from 0, away from x equals 0, I mean, I can, away from x equals 0, is continuous. What does continuous mean? What should it mean? What does it mean intuitively? Tell me again. CJ.
That there is no breaks in the graph at all, that there's a point for every x and y coordinate.
Yep. No breaks. You can draw it without lifting your pen, right? Draw without lifting a pen. Right? These are sort of our intuitive meaning of the word continuous. I can draw the thing without lifting my pen until I get to 0. So except for at x equals 0, I can draw the sine function without picking up the sine of 1 over x. Even this bad function I can draw without lifting the pen. The beauty of mathematics is that once we have some definitions, we can start, we should not need new definitions. We should be able to use previous definitions to make sense of new concepts. So if we want to use these concepts of limits to say something about continuity, how could we do it? Tell me your name. Ari. Yes. So two things must happen. So here's a mathematical definition. So a function f is continuous, is continuous at, mathematicians are very lazy, we abbreviate everything we possibly can. Hopefully you can make sense of it. Is continuous at x equals c if so Hari is saying if the limit as x goes to c of f of x exists, and that means the left limit exists and the right limit exists and they converge to the same thing. And that's it. That's what it means for a function to be continuous. Sid says no. Why? Exactly. It might be a piece. The limit could exist from the left and from the right, and they could agree. But the value at that function makes you take your pen off, put it somewhere, and then move somewhere else. So how do we ensure that we don't lift up our pen? Hold on.
You have to say that f of c exists and is equal to limit x approaches c.
And f of c, which must exist, must equal to this limit. Okay, so two things have to be true, or three, depending on how you count. The limit has to exist, and the value of the function has to be equal to the limit. So you see the beauty of mathematical thinking. We don't need, what does it mean to have a break? What does it mean to draw without lifting a pen? These are new concepts. We don't need new concepts. We have all the concepts we need to define this new notion of continuity. And the notion of continuity, so this is to answer, I forget who asked, maybe Jenny asked about, would I ask things that are more conceptual, like what would be on a workshop assignment? This is totally the kind of thing that I could ask. What is continuity? Continuity, the mathematical notion of continuity is that the limit exists and the value at the function at the point is equal to the limit. Okay, great. All of the functions that you see typically, so usual functions, round up the usual suspects, in other words, polynomials, trig functions, trig functions, you know, sine, cosine, whatever, exponentials and logs. These functions are all continuous in their domain, wherever they can be, in their domains. Okay, so why is the function sine of 1 over x not continuous at 0? It's not defined at 0. 1 over x cannot be defined at 0, so sine of 1 over x cannot be defined at 0. Tell me your name. One more time. How do you spell it? D-R-E-H? T. Theorem. How do you say it? Theorem. Okay, I'll work on it. We'll talk about it. Can you come after and teach me how to say your name, please? I want to pronounce your names properly. So all of these functions, they're continuous. We know what their graphs look like. You never have to pick up a pen. Okay, it's only weird functions that you start encountering when you start doing calculus that might not be continuous. All right. Great. So let's do an example. Whoops. So let's do an example. How could you use such a thing in practice? Whoops. Example. So here's an example. Let's find the limit as x goes to pi over 2 of the function cosine of 2x plus sine of 3 pi over 2 plus x. What is the limit as x goes to pi over 2 of this function? What the hell is the graph of cosine of 2x plus sine? Like the cosine is getting shifted by a, like, the hell does this thing look like? How are we going to see a picture? Yusuf.
It's a -1.
Why did you say that?
Because pi over 2 plus 3 pi over 2 is 2 pi. Sine of 2 pi is 0. So 2x was 0, and 2 times pi over 2 is pi, and cosine pi is negative.
So what you did, that's beautiful. That's exactly right. What you did is you just said, well, what's the value of this function at pi over 2? Why did you do that? You're right to do it. What's the concept we're talking about?
Just plug in values.
Why can you plug in the value?
It's defined.
And continuous. That's the magic word I'm looking for. Because this is just a composition of functions. These are all nice functions. They're smooth. I don't need to know anything about what the curve looks like. I can just plug in. I said at the beginning, limits don't care about the values at the function. That's true. Limits don't care about the values at the function. But if you know that the function is continuous, then you can just plug in the value. Continuous means that the limit does agree with the value of the function. Does that make sense? You see the distinction between those two concepts? Okay, so this is exactly Yusuf's idea, because these functions, this is a composition, composition just means you're taking a function of a function and you're adding things, and this is just taking the identity function, which is a polynomial, which is continuous. You're adding something, then you're taking sine of that, and you're adding something else, then you're taking cosine of that. That's all a composition of continuous functions. We're well within all of their domains are just the entire real numbers, so there's no question about that. Because this is a composition of continuous functions. We don't need to know anything about the graph. we can plug in x equals pi over 2 and get the value of the limit. That's what continuity means, that the limit exists and is equal to the value. So forget about the limit, just work out what the value is, and that tells you what the limit is. CJ. Align. Where's CJ? Okay.
So how would you solve it if you knew that it wasn't anything? Graph it.
With a graphing calculator, I wouldn't want to graph this thing by hand. So if I've asked something like this on an exam, it means here's a hint. You need to, there's a little psychology here. If I'm asking you something, that means it's solvable. That means if you're trying to think of a solution that requires that you have a graphing calculator, it's probably the wrong solution because you don't have a graphing, right? So that's the kind of thing, the kind of game you can play. Yes, the fact that I didn't ask you to open up Desmos and plug this in means that you can do it without that. And so what is it? What could I possibly be asking for? I'm asking for continuity. And the fact that all of these functions are continuous means we just plug in the value at pi over 2, and that'll tell us what the limit is also. Okay, does that make sense? Okay, so just to finish it off, exactly as Yusuf said, this limit is equal to cosine of 2 times pi over 2 plus sine of 3 pi over 2 plus pi over 2, and sine of 2 pi is 0, and cosine of pi is -1. Done. Okay, so the limit is -1. Should we graph this function? You guys want to see what a graph of this thing looks like? All right, fine. Somebody's going to tell me cosine of 2x plus sine of 3 pi over 2 plus x. Okay, it's going to be some god-awful thing. So cosine of 2x plus sine of 3, how do I do pi? Here's pi, that's good, over 2 plus x. I mean, it doesn't look, yeah, that's a weird function. I don't know what the heck is going on here. But we said at pi over 2 is, must be right there. So what point is that? Pi over 2 -1. Okay, so it's some weird, strange function with a weird period and it's moving all around. I don't care. The value is just plug in -1 and that is the limit. Okay, does that make sense? Cool. Moving on. All right. Why are continuous functions nice? Here's one thing about continuous functions. This is called the intermediate value theorem. Intermediate value theorem. Okay, so let's say I have a function f, say f of x is continuous on an interval, let's say a to b. Okay, so the picture in my head is there's some value a and there's some value b, and f starts somewhere and it's continuous. So let's make one more little distinction. This is continuous at a point. What does it mean to be continuous on an entire interval? Exactly. Align. So being continuous on an interval is you're continuous at every point in the interval. Okay, there's no breaks anywhere along the way. So that means I can draw whatever the function is doing from a to b, I can draw like that. Okay, so that's a continuous function on an interval. Here's the question. So here's the value of f of a, wherever it is. Here's the value of f of b, wherever it is. If I take any value y in between, this is called the intermediate value theorem. So if I take a value intermediate between the value that f starts at and where f ends up, what do you think I'm going to say about that? Hold on.
Somewhere in between.
Somewhere in here, you cannot get from a to b without crossing your favorite value y. Okay, that's what the theorem is going to say. The theorem is going to say, then, for all values of y, you know this shorthand for all? Okay, this means for all, if you see this upside down capital A. For all values of y in the interval fa up to f of b, so if this is some capital Y, it's some parameter. what for all values of y, there exists, and there exists is a backwards capital E. You're going to get used to this math shorthand. Okay, for all values of capital Y, there exists some value of C between A and B, so that what? And a value.
Okay, after there was this
Yes,
now, but
there exists C. Oh, I'm sorry. Okay, so this means in. This means in. This is the closed interval A to B. So this is the closed interval A to B.
there's the interval.
Yep, there's somewhere along here is a value C. Okay, this symbol means in, this symbol means for all, and this symbol means there exists. Should I write that down somewhere? Okay, this means in. This means for all, and this means there exists. Say it again. Do you need to know these shorthands? I will not be testing you on your ability to write shorthand in mathematical. But when you get to some arguments, you will start seeing just how many times you write for all and there exists, and you're gonna get very tired of it. You'll be like, wasn't there some shorthand for this that I could throw in there? So these are universal mathematical shorthands. Yeah, so this is like containment. I don't know. Today I can't even see this symbol without thinking, it just means this is contained in this interval. You start mapping these onto, I don't know, words. I'm not a psychologist. Intermediate value theorem. You give me any value in between where you started and where you ended. If you got there continuously, you must have passed through every point in between. Okay, which means for every y in the interval A to B, there exists some value C on the x-axis that, tell me, Caitlin.
The ST stands for.
Oh, ST is such that. Sorry, one more universal mathematical shorthand. Put it here, and ST means such that. See, this is I don't even notice sometimes the shorthands that I'm saying. There's such second nature. So please do stop me, because as a test, Caitlin said, "What does ST stand for?" How many other people were wondering what? Thank you. Okay, that's how many people you just helped. Okay, so please ask if I say a word or use a phrase that I'm so used to using, I don't even notice that it's something I didn't know when I was a freshman in college, right? So such that. Okay, so let's try to read this in English. Let's say we have a function and it's continuous on an interval A to B, A to B. Then for any value of y in the interval f of A to f of B, there exists some value of C in the interval A to B, such that, so that what are we trying to have happen? Sure. Okay, f of C is equal to y. Exactly. F of C is equal to y. Okay, so we found a value of C, so that when I take f of C, so this is the point C comma y, and y is f of C. Okay, does that make sense? If you're going to go from point A to point B and do so continuously, you have to go through all the points in between. All right. Let me give you an example of why this concept is useful. So far, so good. Any questions on this theorem? Makes sense, right? Here's why it's extremely useful. In fact, in real applications, I'll give you not a real application. So here's an example. Does the function f of x equal x cubed minus x minus 1 have a root? You know what it means for a function to have a root. This is a polynomial. Polynomials have roots. It's the same thing as a 0. Does it go through 0 somewhere in the interval on does on the interval 1 to 2. Does this polynomial, now, again, if you go to Desmos and you tell me, give me the graph, you'll see the graph, and the graph will be some kind of cubic. So what's a cubic look like? Something like this, or something like this, or something like this, right? There's all kinds of ways a cubic. So it's a cubic polynomial. Cubic meaning the largest exponent is 3. So it's x cubed minus x minus 1. So I want to know, does it go through 0 somewhere between 1 and 2? So we need a graphing calculator to see if it goes through 0. How could we see if it goes through 0? Tell me again. Rohan. Exactly. Let's work out what f of 1 is. F of 1 is 1 cubed minus 1 minus 1. That's negative 1. F of 2 is, you got it, Shreya? What'd you get? 5? I think that's right. 2 cubed is 8, minus x is 2, minus 2 is 6, minus 1 more is 5. Yep. So here's all we know about this thing. The true polynomial, whatever it does, what haven't I used yet? Red. The true polynomial at 1 is equal to negative 1. At 2, it's equal to positive 5. I don't know anything else about it, but to get from negative 1 to positive 5, and it's continuous because it's a polynomial, you got to cross 0. Okay, so whatever it's doing, the answer is yes, by the intermediate value theorem. Exactly, the intermediate value theorem. Yes, by the intermediate value theorem. Lava. Did I get it wrong? I got it. Viva.
So like, let's say you had these two variables, and like if you plugged in like say the different functions, you plugged in one, you got a positive number, and you plugged in another positive number, but like somewhere between you got across like where it has the x-axis. How do you figure that out?
Excellent question. So Bob's question is, just to repeat it for everybody, suppose we got a positive number and another positive number, and you're looking for a 0. The intermediate value theorem just can't tell you anything. It'll tell you that you'll go between those two positive values, but the function may very well dip down and come back up, even if it's continuous, or it may never cross. You just have no information. So that would be an instance where the intermediate value theorem, it's a great theorem, it just doesn't tell you the information you want. Yeah. Great question. Peter. Repeat that one more time. Let me write it down. It's a good point. If we had f of 1 being positive and f of 2 being positive, that the intermediate value theorem doesn't tell us anything. The intermediate value theorem does not tell us anything about whether f of x equals 0 between 1 and 2, between 1 and 2. So it could be at 1 it's positive, at 2 it's positive, and it just stays positive the whole time, or it could be that it's that it touches just once or goes through and comes back up. We just don't know. All we know, all we know is about the values between where we start and where we end. We might dip below where we start, and we might dip above where we end. The intermediate value theorem can't tell that. Okay. One more time. Andrew.
Would it be accurate as a rule to say that you can use the intermediate value rules at that point exist, but not that it doesn't?
Exactly. Let's write that down. So Andrew's comment, remark. So I don't know what to call this. That is so conclusion, remark. Let's call it a remark. Andrew's remark is that IVT can be used to prove that there is a 0, but not to prove that there isn't a 0. Okay, great comments. More questions? Does this make sense? Yeah. All right. Good. Let's do another example. Let's do more examples. Here's an example. All right, let's think about this. What's the limit? So more on limits. The limit as x goes to 1 of x minus 1 over x squared minus 1. Let's get a little practice. Okay, let's see if we can work this out. Want to take a minute, work on this? Take a minute. Uh-huh. Raga. Yusi. Nimmer. Dan. Doug. Sid. Bye-bye. Okay, any thumbs up? Who's got it? Okay, a whole bunch of you got it. What'd you do? Dan.
Yeah, so the difference squared in the bottom would be x plus 1,
Uh-huh.
x minus 1, and make x minus 1 will cancel out with x minus 1, and you have the 1 over x plus 1, and then you just substitute 1 to get 1 over 2.
Right, so we can't, is this function continuous at 1? So, okay, let's finish saying the thing that that Dan just told us. So you would cancel the top and bottom, which you're allowed to do as long as x is not 1, but we don't care about the value of x at 1. So where x isn't 1, so we're allowed to cancel. Okay, so cancel it, this cancel since x is not equal to 1, right? Limit only cares about nearby values. And then this becomes 1 over 1 plus x. And now I really can plug in x equals 1 and I get a half. Okay. Right? Everybody see that? What does this function look like? I'm curious if Desmos, how Desmos plots it. So like this function is the same thing as this function 1 over x plus 1, right? Which is going to be a hyperbola thing. Let's see. I'm curious. So what was it? X minus 1 in parentheses. Uh-oh. Yeah, there's an x minus 1 open. Yeah, good. Divided by x minus 1 squared. X squared minus 1. Great. Okay, and we were asking about the limit as x goes to 1. So here's our hyperbola with an asymptote at -1. This is -1. I can't point. I don't have a pointer and it doesn't. So as you go to -1, this thing is blowing up. As you go to +1, you did it. Wait. Come on. I have to touch. Wait, my finger. Yeah. I saw it for a split second. You saw it too, right? Yeah, that's a good. Right there. It knows that the value at 1 is undefined, but it won't show you that because it's showing you what looks like a nice continuous curve. Okay. So, so this gives us another concept, which is a continuous extension. So, okay, the true graph, the graph of x minus 1 over x squared minus 1 looks like this. There's this asymptote at -1, and then at 1 there's no value, although the value would be a half if there was a value, and then it sort of does that kind of thing, right? That's what we just saw in Desmos. So this value is it's kind of a removable value. This is removable value. So we can define something called a continuous extension. So definition, if the limit as x goes to c of f of x exists, but does not equal f of c, either because it doesn't equal f of c or because f of c is not in the domain. Like I could have given this another value, some random value, and then it still wouldn't be continuous. We can define what's called the continuous extension. Continuous extension. Okay, so that'll be a piecewise function. Sorry, just a second. Okay, what do I mean by continuous extension? There we go. So in this case, I could define another function, let's call it g of x, and I'll define it piecewise. I'll make it x minus 1 over x squared minus 1 if x is not equal to 1. Okay, so that's exactly what our original function was. And I'll extend the definition of the original function by one value, which is if x is equal to 1, I'll set g to be, 1/2. This 1/2, which was the limit, I'll set g to be 1/2. So I fill in that gap. This 1/2 fills in the gap. And now the function becomes continuous at 1. So this g is the continuous extension of this original function. Does that make sense? Will? Right before f of c not equals. Oh, that's an attempt at a not equals sign. Let me make it better. If this f of c does not equal the limit, okay, if this limit exists but is not equal to the value, we can force it to be equal to the, we can like make a dot there to make a continuous extension. Okay, does that make sense? All right, so now let's go all the way back to what we were doing last time. Unless there's anything else I needed to say before. Yes, Ying. Why do we need? Why would we want to do such a thing? I'll show you right now why you would want to do such a thing. Okay, so why you would want to have what's the purpose of having continuous extension? I'll tell you right now. So this g of x, by the way, when you make this g of x, even though you define it as a piecewise function, it's literally equal to another function, which isn't piecewise. 1 over x plus 1, exactly, 1 over x plus 1. So this 1 over x plus 1 really is defined everywhere. And that's what Desmos is graphing, even though it knows, Desmos is very smart. It knows that exactly at 1, it's undefined. I can't divide 0 by 0. So that was this original function, which has this singularity, this place where it's not defined. And then we can redefine a new function by extending extending continuous. Okay, why am I telling you this? Remember what we were doing at the end of last class. So last time, we were trying to understand what happens to the slope of the sine function near 0. Slope of sine near x equals 0, right? So the sine function is doing this kind of thing. X equals 0 is right here. Yes, Raga? It's still not defined on -1. That's right. It's still not defined on -1. I guess if you want to, yeah, we can add as long as x is not 1 or -1, then it's equal to this. And if it's 1, it's equal to this. Alternatively, if I didn't add this in here, you would try to put in -1 into the denominator and see, oh, I'm dividing by 0. I can't do that. So just because it's defined piecewise doesn't mean it actually, the value of this thing exists everywhere where you set it to. Just like when I defined this function, when I defined it originally, when we first said, okay, look at this function, I didn't say what the domain was. You have to infer the domain from where you're not dividing by 0. Does that make sense? So I'm still asking you to infer the domain. Well, here I'm making the domain explicit. But if I didn't put the second condition, you would say, okay, what must the domain be? I can't divide by 0. Does that make sense? So yeah, it's probably good practice to put both of them in, but if you didn't put both of them in, that's still okay. What we're really talking about is this continuous extension. Good? Okay, so last time we were trying to understand the slope of the sine function near x equals 0. So we took some nearby value theta. This was the point theta comma sine of theta. And so the slope near 0, so slope near 0, or the slope of the tangent line at 0, or tangent line at x equals 0, because the secant line is going to approach the tangent lines, right? Secant means crossing through 2 points, not that it's the secant function. The slope near 0 is the limit as x goes to 0, either from above or from below. It turns out by the odd, because sine is an odd function, if you know the limit from above, you also know it from below. The limit as x goes to 0 of sine x over x, or the limit as theta goes to 0 of sine theta over theta, same thing, right? I'm just reminding you what we were working on when we stopped last time. Now, what we saw, we used a little bit of geometry. What we saw was that if you set up your unit circle, and here's your angle theta, I guess I really do want to call these thetas. It's a dummy variable. You call it whatever you want. Call it the queen. Oh, that's blasphemous. Anyway, make sure rest in peace. Okay, so theta is here, right? We looked at this triangle as opposed to this arc, the full arc, as opposed to, if I extend this tangent line, this bigger triangle. You guys remember that? Should we go over that calculation again? Yeah, okay, fine. Let's go over that calculation again. So let me, okay. So what's this length? What's this vertical height? Sine. This is the unit circle. So this is sine. This is sine theta. This length, cosine. This arc length, just out of curiosity, theta itself. And what about this length here? Tan. Good. Good. Tan theta. Here's our right triangle. Here's our 1 by tan by secant right triangle, as opposed to our sine by cosine, and the, well, not by, but the hypotenuse is 1 triangle. Great. Why is this tan theta? Okay, so if you look at this angle, theta, and you have a right triangle, the tangent of theta is opposite divided by adjacent. And adjacent is 1. So opposite has to be tan. This is why it's called tan. The reason it's called the tan function is because when you take this tangent to the circle, it's the tangent to the circle, and that's its distance. And the reason this is called the secant is because this distance is the distance through this line is a secant to the circle. The x-axis is a secant to the unit circle. It crosses it. Doesn't cross it tangentially, it crosses right through it. Okay. We saw these things and we compared 3 areas. There was the orange area as compared to the green area as compared to the purple area. Okay. And what we saw, so what's the, oh God, you can't see anything now. Can you? Orange. So what was orange? Orange area. Let me stay with the color scheme. The orange area is this triangle. What is it? What's the area? Dan. Exactly. Base times height. Base is cosine. Height is sine. 1/2 base times height. So this was 1/2 base times height. The orange area is less than the green area. The green area is slightly bigger, right? The green area is this sector. What's the green area? Well, the entire unit circle would have area pi r squared, which is pi, the radius is 1 squared, that's a 2, 1 squared. But we're only taking theta out of the 2 pi possible radians all the way around. So we get theta over 2 pi. Okay. This is ringing bells. This is what we did last time. And that was bounded by the big triangle. The big triangle is purple, which is 1/2, 1/2. Well, it's a triangle, so I have 1/2 base times height. My base is tan, my height is 1. 1/2 tan 1. 1/2 tan theta. Okay. This is the kind of thing that when I said like it takes people 100 years to find this kind of stuff, this is the kind of thing that takes people like 10 years to figure out. This kind of geometric proof. This is not what I would be asking you to find something like this on an exam. Okay. But so what can we do with it? We can there's 1/2 everywhere. Let's do a little cancellation. This 1/2, that 1/2, that 1/2. There's a pi on top and on bottom. That tells us what? That theta is bounded by tan, which is sine theta over cosine theta, and is bounded below by sine cos. Sine theta, cosine theta. By the way, what is sine theta, cosine theta? What's another expression for this? Sine of twice theta, except sine of 2 theta is 2 sine of theta cos theta. So it's half of sine of 2 theta. Okay, I'm just reminding you some double angle formulas, making sure that those are in there solid. Okay, you see how I got from here to here? Great. Let's divide both sides by sine. So I have cosine is at least theta over sine theta, and is at most 1 over cos theta, which is secant theta. Right? And this is where we used, so if, and let's, since we're interested not in theta over sine theta, but sine theta over theta, if I reverse both sides of that, I get sine theta over theta is at most 1 over cosine, which is secant, and is at least 1 over secant, which is cosine. Okay, so far so good. So this is the thing we're interested in. We're interested in the value of this at theta equals 0, and we've sandwiched it between these two functions. And then we learned something called the sandwich theorem, or I call it the squeeze theorem. So the squeeze theorem, some people call it the sandwich theorem. THM is theorem. That one I think is not so hard. If you have one function that's always above and one function that's always below, and they have the same limit, and you have something that's trying to squeeze in between, it has no choice but to have the same limit. Okay, let me write that in words. If I have a g is my bottom function, h is my top function, f is the function. If g of x is less than f of less than or equal to, it doesn't have to be. I mean, the fact that it's a strict inequality is not important. Is less than or equal to h of x near some point near x equals c. Let's give this some axes and call this c. And the limit as x goes to c of g exists and is equal to the limit as x goes to c of h. So g has a limit, h has a limit, and those limits agree. If those conditions are met, then who's saying that? Nimir. Exactly. The function f has no choice but to exists, and is equal to these other guys. Okay. How are we going to apply that here? What happens to cosine at near 0? Yep, the approach is 1. So cosine looks like this. This is cosine. What happens to secant near 0? It's 1 over cos, so it does this. That's secant. So whatever this function is doing, it has to sneak in between. So whatever this function is doing, it has to sneak in between, which is how we know that this function sine theta over theta has a limit. So by the squeeze theorem, by sandwich theorem, the limit as theta goes to 0 of sine theta over theta is equal to 1, the same value. Let me just show you a picture of that just for a second. If I have cosine of x, there's our cosine. And if I have secant of x, 1 over cosine, that's what that's doing. And then if I put here sine x over x, sine x divided by x, whoops. Yeah, no, delete. I don't know how to use this damn thing. Okay, forget it. Try a new one. Sine x over x. There it is. It squeezes in between. Okay, and now we can do one last thing. Sorry, Peter. Yeah. What does what multiple times? Yes, but only near this one point is the inequality true. So the inequality that sine x over x is between cosine and secant. Use the fact that theta was small. Once you get outside of the range of this picture, once theta gets large, this geometry no longer applies. Okay, so this is all in the neighborhood. And let me just say one last thing, which is then that we have a continuous extension. So sine x over x has a continuous extension, and then we're done. A continuous extension, which is the function g of x, which is sine x over x if x is not 0, and if x is 0, 1. Plug in that one value, and now we have a nice function, sine x over x, whatever it is. It has this one value plugged in. Okay. Have a nice weekend.